I'd like to talk about quantum numbers, which we can think of as addresses for electrons. So let's envision we have a street, and it's a small street, and the street is only big enough to hold one house. We're going to name our streets with the letter N, and so where N is equal to 1, we can only have one house. When N is equal to 2, we can have more houses, and those houses can actually get bigger. So we could have a small house, and we could have a large house. Now this large house, we're going to have different names for these houses. One house here, the small house, we'll use an S, and for the larger house here, we'll call that P. Now the difference between the two houses is that the small house only has one room, but the larger house has 3 rooms, 1, 2, 3. If we go up just a little bit further to the next street, we see this street can have more houses, and this house here is going to be even larger. This house can have 5 rooms in it. I'm sorry. Yeah, this house can have 5 rooms in it, like so. Okay, and we could keep on going here, but I think this is going to show us the gist here. Let's say that each house can have a maximum occupancy of 2 electrons per room. So for this small house on the small street, we can only put 2 electrons in here, and we're going to name these electrons as spin up and spin down. We don't need to worry about those names just yet. This house can also have 2 because it's a small house, but the larger house can have a total of 6 because it's got 3 rooms. And as we would continue on in each one of these, we would notice the D. Oh, I'm just noticing now that my D only has 4. So 1, 2, 3, 4, 5. It should have 5 in there. And there we go. Okay, so we should get the idea that bigger streets, bigger N, we can get more houses, and the houses are going to get bigger and bigger as we move along. Turns out that there's some mathematical guidelines that help us understand what we can put where in our various streets. We've got N, and N can be any value that's an integer, 1, 2, 3, and it can go all the way up to infinity, although we probably won't go that far. Okay, let's talk about the number of houses that we have on each one of these streets. First off, instead of saying S, P, and D, I'm also going to call these names 0, 1, and 2. And it's just nicknames, right? The S and P and D are actually nicknames for the numbers 0, 1, and 2. So the street names we're using L, and the house names, I'm sorry, street names we're using N. So house names we're going to use L. Notice how when we have when N equals 1, so on the smallest street, we could only have an L of 0. When N is equal to 2, we could have an L of 0 or 1. We have both of them. And then when N equals 3, we could have an L of 0, 1, or 2. Notice here how L starts at 0 and goes all the way up to N minus 1. So that tells us how many houses we can have on those streets. I'm going to erase this stuff here to make some space. And now let's take a look at the number of rooms. The number of rooms, we're going to call that symbol M sub L. And let's relate the number. We notice that the number of rooms obviously is based on the size of the house. So when we see here, when L is 0, then the number of rooms is 1. When L is 1, the number of rooms is 3. And when L is 2, the number of rooms is 5. One way we can indicate this, especially with the way we've numbered the rooms, I'm sorry, the houses 0, 1, and 2, is that we can say that the rooms go from minus L all the way up to positive L. And let me show you what this means. Here, if for this orbital, if the L is 0, then negative 0 to 0 can only be 0. So that's kind of bizarre, but let's take a look at P. If our L value is 1, then the different rooms can go from minus 1 to 0 to positive 1. Notice how we're just incrementing. We're starting from the negative value of L and increment until we get to the positive value of L. And there turns out to be 3 rooms, or 3 digits, to indicate the 3 different rooms. If we do that one more time here, with the D, we would see minus 2, minus 1, 0, 1, and 2. Again, from the negative side to the positive side. So with these 3 values, we're going to see, let's see, N, which is the principal quantum number, L is the angular quantum number, and M sub L is the magnetic quantum number. Lastly, if we recognize that what I'm referring to as streets is actually a measure of the energy of an electron in an atom, we see that the quantum numbers give us a way of identifying the amount of energy that an electron has at different positions within the atomic structure.